When Edward Pickering escorted Anna Draper, daughter of a former Harvard president, widow of Dr. Henry Draper, one-time amateur astronomer and soon-to-be benefactor, into the main building of the Harvard College Observatory, the two passed through the calculation room. Here they found a number of assistants busy at various tasks. Some were performing detailed calculations on the previous evening's positional observations of various celestial objects in order to correct for the atmospheric refraction, or bending of the starlight as it passed through the Earth's enclosing cocoon of gases, in order to arrive at the object's actual position on the celestial sphere. Others were transcribing data on the brightness or apparent magnitude of various stars into tables and comparing them with previous measurements to see if there had been a change in the object's output of light, indicating that it was a variable star. A few were seated at tables, peering at glass plates set on upright stands that had backs etched with precisely spaced lines that made measuring the positions of the stars on the plate easier. At the bottom of each stand was a thin mirror that reflected the light from the room's large windows onto the plates so that the spectra also captured in the photograph could be more easily read by the examiner. As they had walked through the halls of the facility, Pickering addressed each member of the staff they passed respectfully. Senior astronomers were referred to as Professor Rogers and Professor Seal, and assistants as Mr. Wendell and Ms. Fleming. While he removed his hat for the ladies of the observatory as he greeted them, it was clear that they were not just visitors or custodial staff, but rather engaged in the scientific work of the observatory in an integral fashion. It surprised Mrs. Draper to see that half of the calculational assistants were, in fact, women. As they entered Pickering's office, she asked him if having women work in observatories was commonplace. Pulling around a chair for her to sit in, and then taking his own place, Pickering told her that it wasn't, but that at Harvard he had instituted the practice soon after he had taken the post as director and had never had a reason to regret it. At present, he told her, there were 6 ladies employed in the work of analyzing the observations of the astronomers, all doing exceptional work. Among them was Selina Bond, the daughter of the observatory's first director, William Cranch Bond, who assisted Professor William Rogers in calculating the adjustments in stellar positions for an international mapping project administered from Germany. There was also Anna Winlock, the oldest daughter of Pickering's predecessor. Having grown up in the observatory, Miss Winlock knew its methods and rhythms as well as any undergraduate student might. And then there was Mrs. Fleming, whose exceptional work had led Pickering to elevate her to among the most trusted of the calculators. Pickering explained that while he did not subject the women to the fatigue of nightly observations, nor the winter cold of the unheated observatory domes, their willingness to undertake the unexciting but vital work of reducing those observations to the numbers that represented brightness and position in ways easy to communicate with other professionals made their inclusion absolutely necessary, especially given the low pay and constrained budget of the observatory. Anna Draper, long her husband's willing assistant in astronomical work, nodded approvingly and said, "Well, perhaps we can find a way to help with that."
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 3, Finding Our Place. Episode 35, By the Letter. In our last episode, we covered the beginning of the work done at the Harvard College Observatory under the direction of Edward Pickering. The role of women in this research and the efforts we will discuss in this episode cannot be underestimated and will form much of the content herein. The first thing, though, that has to be said is that it is unlikely that much of the work done at Pickering's urging would have been possible without the generous contributions of two very wealthy women. As we've already discussed Anna Draper in some detail, let me say just a few more words regarding her relationship with the observatory. In addition to her initial endowment for the Henry Draper Memorial, she would, in time, donate the instruments of her departed husband's private observatory to Harvard. These instruments would vastly expand what Pickering's staff could do and, in time, would allow him to start the observing effort in Peru. Additionally, she would continue to make financial contributions to support the work of the observatory throughout her life, especially in providing funding to hire computational assistants, as well as for additional instrumentation. The other figure we should mention is the Manhattanite Catherine Wolfe Bruce. Ms. Bruce was a painter and a patron of the arts who had inherited the fortune her father had made in printing. At the age of 73, her long-held vague interest in astronomy seems to have been crystallized by a doleful article by the astronomer Simon Newcomb of Johns Hopkins University. Newcomb, apparently unfamiliar with the burgeoning efforts at Harvard, had predicted that there would be no new advances in astronomy, only more observations of the same known objects or of new comets found to be much like those previous. However, she soon found herself captivated by the rise of photographic images of the heavens being produced at Harvard, and so threw her substantial financial resources behind the efforts being undertaken there. In time, she became Pickering's other great patron, paying for the 24-inch telescope that would be installed in Peru, as well as endowing a number of other efforts, including a large number of one-time grants to astronomers around the world to finish observing projects, get papers published, and anything else to get over the proverbial hump to get new research out into the scientific community. Bruce's support would both make sure that the Peru observing station was a world-class facility and that there would be enough calculators back in Cambridge, Massachusetts to gather the needed data that would eventually pour in from that facility due to the efforts of first Pickering's brother William and then the station's indefatigable director, Solon I. Bailey. With these acknowledgments made, let us turn to the continuing scientific work of the observatory. As the Draper Memorial Catalog effort got underway in 1886, there were 14 female computers serving under the supervision of Williamina, or more commonly, Mina Fleming. The group had a strong sense of camaraderie and worked rapidly to reduce the data being gathered nightly from the large photographic plates being made. The computers worked in pairs, one examining and measuring while the other recorded all of the data relayed by the first. For 2 years, this continued with great regularity as the women were all of about the same social standing in the culture of New England, and thus Mrs. Fleming's age and life experience elicited respect from her younger peers. However, in 1888, this would change somewhat with the arrival of the first female calculator that actually held a bachelor's degree and also a higher social standing than most of the calculators. Antonia Maury was the daughter of the Reverend Myton Maury, and a descendant of the powerful and connected Maury family whose lineage stretched all the way back into colonial times. She was the granddaughter of John William Draper and thus the niece of Henry Draper. In 1887, she had graduated with honors, earning bachelor's degrees in astronomy, physics, and philosophy from Vassar College, one of the number of all-women's institutions of higher education that were springing up throughout New England and the Middle Atlantic states during this time. While at Vassar, she had studied with the noted American astronomer Maria Mitchell, the first American woman to work as a professional astronomer and also the discoverer of a comet. Upon Antonia's graduation, Anna Draper had written Pickering asking if a place could be found for her at the observatory. While Pickering would be thrilled to have the young woman join the team, he was in a bit of a quandary. He didn't need another full-time, full-level astronomer, but it seemed a bit beneath someone of Murray's standing and education to be a mere calculator. While it took some doing, Pickering finally came up with a solution. which was to have her do something that would today be the kind of thing a research professor might have a graduate student do. What he did was he gave her the spectra of the brightest stars that they were photographing at the time for more detailed analysis. Now, these spectra had been taken by the recently donated Draper 11-inch reflector, which, unlike the observatory's other scopes, focused the light of just one star through its prism. This created a much larger spectrum that allowed for a more minute analysis. For example, when looking at the spectrum of Vega, Maury's uncle, Henry, had photographed just 4 lines in the blue end of the spectrum in 1879, and then 10 when the procedure was repeated with a better type of photographic plate in 1882, just before his death. In 1888, just 6 years later, Maury was able to examine over 100 lines in that same region. So, what was she doing with these specific spectra, which would end up numbering at just about 681 stars? Well, the first thing she had to do was very accurately measure the positions of the absorption lines and any emission lines if there were those, and then convert those to wavelengths. Once she did that, she then had to classify each star according to the scheme developed by Mrs. Fleming. However, and here's where Pickering's genius in allowing his workers some flexibility comes in. What Maury had in these new and large spectra was a great bit more detail in terms of the specific characteristics of the lines in terms of their appearance in the spectrum. Some were thin, while others were thick. Some had sharp edges to the lines, while others were hazy. So why was this important? Well, if you'll recall from our last episode and our example where we used the idea of bird identifications, in a sense, what these examinations of spectra were trying to do was figure out how to differentiate between one species of a star and another, if you will. Now, if you already know which characteristics are important, say things like beak shape and wing length from birds, then it's much easier to do that sort of classification. And it's much easier to understand why those characteristics are important. However, if you're just at the starting point of figuring out what makes one bird different than the other, you probably want to note every single difference you can from one type of bird from the other that you either observe or capture. This is really what Maury was doing with these stars and the spectra that she got from them. Fleming had, in a sense, done a classification on the gross anatomy of the spectra of the stars. Now Maury is looking at the much finer structure of those spectra. With the insight of a scientist who knew that having different minds tackle the same problem from different angles, Pickering gave Maury the freedom to come up with her own classification system that took into account those shapes of the spectral lines as well as their positions in the spectra and their intensity. Her classification would exceed Fleming's in the number of categories, 22 to Fleming's 16s, but she would also subdivide each category into 3 subcategories that were based on the line shapes. We'll return to this in a little bit. While this project was underway, there was another thing that had caught Pickering's attention. In 1887, among one of the early Draper memorial plates, he saw something really weird. The plate had been taken of the portion of the sky that contains what we refer to as the Big Dipper, or Ursa Major if you'd like. Among the stars captured in that image, along with its spectrum, was Mizar, which occupies the bend in the handle of the Dipper. For my Northern Hemisphere listeners, you can go out tonight and take a look if you have clear skies and are so inclined. Now, Mizar is actually part of a double star system, with a second star that you can just barely see with your naked eye if the seeing is good, that's known as Alcor. This made getting separate images of the two spectra a bit tricky, but what Pickering noticed in the Mizar spectrum was that the Fraunhofer K line was doubled, meaning that there were 2 seemingly identical lines side by side in the spectrum, unlike what you would normally see, which would just be one single K line. Intrigued, Pickering went to find the spectrum the next time the region of the sky was photographed, and to his surprise, the K-line doublet had actually disappeared, replaced by that expected single K-line. Very odd. Pickering kept looking for it in subsequent images, and he designated that Mizar be periodically photographed with the Draper 11-inch. So it was that on January 7th, Antonia Maury found that doubling taking place too. This was a huge revelation as it confirmed that the spectrum alternated between having a single and double K-line. Now the question was, why was this happening? Why did the line change? And as it was changing, was that change in fact regular? Now, Pickering had an idea of what was going on, though he wasn't ready to share it outside of the close-knit community of the observatory. What he suspected might be the case was that Mizar, as seen through the telescope, actually consisted of two more or less identical stars so close together that the telescope, even with its magnification and added light gathering power, was unable to distinguish between the two. According to Newton's laws, these stars had to be orbiting each other, as was the case for the various visual binaries that had been known about for quite some time. So, let's try and visualize this just a bit. As a way of sort of getting a sense of this in your head, think of a scenario where you're watching two people on either ice skates or roller skates that are holding hands and are spinning or circling around a common center. Now, at some point during the spin, you'll see one skater, say the one on the right, moving away from you while the skater on the left moves towards you. A quarter of a turn later, you'll only see one skater while the other is hidden from view behind the skater you can see. A quarter of a turn later, you again see the skater on the left moving towards you and the skater on the right moving away. Finally, a quarter turn later, you see the other skater in front and the first skater is hidden. Okay, in our example so far, we're assuming we have two skaters that look different from each other. What if they were in fact twins and they were both wearing the exact same kind of clothing? Well, now you're going to have real trouble figuring out what's going on, as the brain will have trouble sorting out what it's seeing, and as psychological studies tell us, it might misinterpret the rotation direction or rate or any number of other things. So in this situation, what would you do? Pickering's mental picture is that the stars, which are pretty close to identical, are acting just like this identical twin ice skaters thought experiment, with the added complication that they're too far away to tell apart. This is where the Doppler effect becomes really, really important. So, in Pickering and Maury's minds, we've got two stars revolving around each other, much like our skater example. If this is the case, when one star was moving towards the observer, the Doppler effect said that its spectrum would be shifted a little bit towards the blue end of the spectrum, while for the other star, the Doppler effect would shift that star's spectrum a little bit towards the red. This created the K-line doublet. A quarter of a turn later, not only would one star be blocking the light from the other, the two stars would no longer be moving towards or away from the observer, but instead would have velocities at right angles to the line of sight, and so there would be no Doppler shift at all, and the spectrum would show a single K-line. If this was the case, the doubling of the K-line would happen every half of a revolution of the stellar pair in a regular fashion, with a definite, regular time spacing between the doubling events. On May 17th, they saw the doublet appear again after photographs taken in the days leading up to the event showed the K-line getting fuzzier and fuzzier. This confirmed their hypothesis, and Pickering wrote a short paper about this discovery that he sent to Anna Draper, who carried it with her to be read by George Parker at the annual meeting of the National Academy of Sciences in Philadelphia that November. In it, he credited Miss Maury for her careful study of the spectra taken as being instrumental in the results being reported. A few weeks after this, shortly after a visit from Mrs. Draper to observe the line doubling of Mizar, Maury found the second case of line doubling in the star Beta Aurigae. Shortly after this, a third example was independently discovered by Hermann Vogel at the Potsdam Observatory. These spectroscopic binaries, as they were called, were important in that they increased the number of stars for which the mass could be determined. By knowing the period of revolution and the velocity of each star, something that could be determined from the amount of Doppler shift in the line doubling, the mass of both of the stars could be determined with fairly high accuracy. This will be very important down the road just a bit. When Draper included Antonia Maury's discovery in the 4th annual report of the Draper Memorial Catalog in 1890, something that was sent out to everyone who might be interested, it was published in a wide variety of journals, including Britain's Nature. One of the responses to the news came from astronomer and military engineer Colonel John Herschel, grandson of William and son of Sir John, who wrote to congratulate Miss Maury on, quote, having her name connected with one of the most notable advances in physical astronomy ever made, end quote. Only 26, Antonia Maury's future seemed full of promise. As we proceed forward at this point, one of the difficulties we run into is that there are now sort of two research tracks that we really need to follow. One will be a continuation of the spectral classification work, while the other will grow out of the photometric work being done with both the meridian photometer and by examination of the photographic plates now accumulating in vast numbers at the observatory. This second bit of work would center on the identification and characterization of variable stars. It should be noted, however, that at times the two projects would intertwine, as in the case of Mina Fleming's ability to identify likely variable stars from similarities in their spectra. However, for the rest of this episode, we'll follow the spectral classification work and then return later to show how that variable star project would be really important and take up more time and resources as it proceeded forward. As the observatory moved beyond the publication of the Draper Memorial Catalog in 1890, Pickering hoped to publish Maury's classification work by the end of 1891. However, Maury's complicated scheme was proving to be somewhat difficult to work with, as it required multiple checks of many different characteristics in the spectrum itself. This delay frustrated Pickering, which in turn led him to put pressure on Maury. Maury had taken a second job as a teacher at a nearby school, and this also took time away from her observatory work. Pickering, though, could hardly complain, as the wages he paid were rather paltry, especially for a young woman who sought to live independent of her family's wealth. Nevertheless, he began to look over her shoulder a bit more, which only added to the problem. Soon the situation became unworkable, and Maury indicated that she'd like to leave the observatory. Her only condition was that she be allowed to finish her project and have it published under her name. Pickering, for his part, was all for that, but he was left wondering if the work would actually ever get done. As she departed with the promise to finish up her publication in the near future, the observatory began to receive plates in large quantity from the Arequipa station in Peru. The increased volume of plates necessitated the building of a brick fireproof building to store the accumulating record at the heavens. This construction was completed at the end of the year, and most of the computers were moved with the plates into this new building. Shortly after this, Miss Maury returned from a period of travel to finish her work before taking a more permanent leave. In 1893, the astronomer George Ellery Hale organized what is known as the Congress of Astronomy and Astrophysics. Hale had been an advocate of founding an American professional organization and had decided that the 1893 World's Fair in Chicago, known as the Columbian Exposition, would be the perfect place to gather the astronomical community of the United States together for a professional meeting and conversations on how to get this whole thing started. Of course, as the leading observatory in the country, Harvard was invited to submit as much as they wanted to the meeting and participate in all of the organizational conversations. As a side note here, the Columbian Exhibition was perhaps the most notable for its display of alternating current technologies perfected by Nikola Tesla and George Westinghouse, along with the display of the world's largest Ferris wheel, a carnival attraction that had the unexpected consequence of showing many people a world they had never seen by elevating them to an altitude that allowed them to look far beyond the 20-mile radius beyond which they rarely traveled. Pickering was invited to prepare an exhibit of the observatory's photographs and to give the opening address of the meeting, as well as a public talk that included the words, quote, "Our only knowledge of the constitution of the stars is derived from a study of their spectra," end quote. Mina Fleming also prepared an invited talk that spoke to her desire to see the principle of feminine equality applied within the discipline of astronomy. She wrote in this end, quote, "While we cannot maintain that in everything woman is man's equal, yet in many things her patience, perseverance, and method make her superior. Therefore, let us hope that in astronomy, which now affords a large field for woman's work and skill, she may, as has been the case in other sciences, at least prove herself his equal." End quote. The exhibition served as a focal point for the women's suffrage movement in the United States, and at the time, both Julia Ward Howe and Susan B. Anthony made presentations, and a specific women's building was designed by Sophia Hayden, the first woman to earn a degree in architecture from MIT, as part of the exhibition's structures. Unfortunately, though, due to the installation of the new Bruce telescope for testing before it'd be sent to Peru, only Pickering was free to make the trip to Chicago, and so the women calculators of the observatory were unable to participate in the activities of the suffragettes or anything else. Perhaps Pickering's announcement on November 15th of that year, after extensive testing of the telescope, that Harvard was now in possession of the world's foremost photographic astronomical instrument, was of some compensation. Well, that and the discovering of a nova made by Miss Fleming just 2 weeks earlier. She had been poring over these new photographic plates that had been sent from Peru when she located a star with a very odd spectrum. It possessed a dozen prominent hydrogen emission lines, bright upon the rainbow background. The photograph had been taken on July 10th, and Pickering immediately wired Solon Bailey via telegraph to take additional pictures of that region of the celestial sphere, invisible, or unavailable, I should say, to the northern hemisphere defined by the constellation of Norma, or the Surveyor Square. The previous nova that had been observed, having occurred in 1891, had been spotted by a Scottish amateur astronomer whose timely notification of the Astronomer Royal allowed photographs of its spectrum to be taken at Oxford and Potsdam. Fleming compared these with Nova Normae's spectrum and found them to be almost an exact match. In the publication that followed, Pickering suggested a new class of stellar objects based on these spectral similarities. While he suggested thinking of novae as the ultimate variable star, it would be the idea that stars came in different classes defined by specific emission features in their spectra that would be the thing that would stick down the road. At this point, I would like to break the narrative just a bit for a moment of, I guess I'd call it, personal reflection. What we're about to undertake here is a journey into uncharted waters filled with various islands full of wonders and marvels. The problem I've been struggling with for over about the last week has been how to tell this part of the story. Up until now, things have been pretty linear and somewhat straightforward. However, with Antonia Murray's spectroscopic work, that's really going to change. In fact, in the period between, 1895 and about 1910, things are really going to get very, very muddled before they sort of get sorted out a little bit. Now, one way to tell this story would be to hit the high points, ignore the confusing bits, and get to the point where it all sort of gets ironed out enough that forward progress is once again made. To be honest, that's the way it's done most of the time. The reason for this is that it's the knowledge of how stellar spectra are classified that's the important point, and so you get through to that and then just keep moving. And you do that so that you can get to sort of understanding what's going on. For us, though, one of the goals is to try and see how science actually got done. And so, because of this, we really want to dive down into that confusion for a bit to see why it came about, and then that'll give us a better setup for how it gets resolved. By doing that, we'll get a greater insight into the actual practice of science. Or at least, I hope we'll get an insight into the actual practice of science. Who knows, maybe I'll make it all just so much worse. So, with that in mind, we're going to head into uncharted water here a bit and see what we can learn. If you find yourself getting a little confused or overwhelmed, in the immortal words of Douglas Adams, don't panic. Take a deep breath, find your towel, dab your brow, and just hang in there. I have to tell you that I've been wrestling with this whole thing for the better part of this last week, and there have been times when I've really struggled to make sense of everything that was going on. It's a tough thing due to the fact that we are going to have several different people doing different but intersecting things. And they're all going to have different ideas about this really not very well-defined problem. So, in short, don't give up on this episode if you start feeling lost. That sense of cognitive dissonance you're feeling is probably exactly what, probably a dozen different researchers all over the United States and Europe were feeling at just this period of time. So, let's recap a few things we'll need to remember as we head into the maze. First, there were a couple of stellar spectral classification schemes out there already. First, there was Secchi's Class 1 through 5 Roman letters approach. This had sort of been expanded upon by William Huggins in one way and Hermann Vogel in another, but both were working more or less from his ideas. Next, there was Norman Lockyer, who in addition to discovering the one absorption line for helium in the spectrum of the sun, had put forward his ideas that supported his meteorite hypothesis idea of star formation. Finally, in terms of background, one thing we need to add to this is a group of stars known as Wolf-Rayet stars. Back in 1867, the French astronomers Charles Wolf and Georges Rayet had reported observing 3 faint stars in the constellation of Cygnus that had, very peculiar spectra. Rather than the typical absorption spectra, each of these objects had a continuous emission spectrum with several bright emission bands, with one of the bands in the blue portion being particularly broad and bright. Vogel had followed up on these observations, confirming the general nature of them, but showing that the blue lines occurred at slightly different wavelengths for one of the stars. Now, more recently, there had been a new avalanche of work. There was, of course, Fleming's massively expanded classification scheme published in 1890. I say massively expanded due to both the much larger number of stars in the survey and the structure of the system itself. As you will recall, she used an alphabetical designation with letters A through O, where O contained the Wolf-Rayet stars we just mentioned. Here the emphasis was on the presence of certain lines, only without much of an attempt to take into account any sort of stellar evolution hypothesis or scenario. It was, in the words of one commentator, an entirely empirical system with no attempt to be explanatory. This was the environment in which Maury's work had been started. However, as is often the case, when things are in flux in the sciences, as was certainly the case here with rapid improvements in all of the associated technologies, discoveries come fast and often force those attempting to work in a field to make changes in order to keep up. As we said earlier, Maury was asked to make measurements of better and more detailed spectra of bright stars in the northern hemisphere, 681 in all by the end of the project. As she did this, she was given free rein to create her own classification system, something she decided to do. For this system, though, she not only looked at the placement of the various spectral lines, both absorption and emission, but also the spaces between them and what the lines themselves look like. This led her to propose a system of 22 different categories and then up to 5 different subcategories for each of those. The first set, in the original 22, was an expansion of Fleming's scheme with some important modifications we'll discuss in a moment. The subcategories, labeled with lowercase letters, had to do with the specific shapes of the lines, with the A designation meaning the lines were sharp and often very strong and kind of broad. The B lines were relatively wide, but their edges were hazy or wavy. And the C lines were very sharp and very, very narrow in the spectrum. In some cases, stars might show a combination or something intermediate, and so there was also an AB and an AC designation, and that gives you those 5 sub-classifications or subcategories. Now, to get a better picture, or maybe to make things a bit more confusing, let's look at those main designations. Maury chose to go back to using a Roman number labeling protocol here, but she also rearranged things a bit. In what would be the most important example of this, she created 5 classes of stars from those growing number of stars that showed odd spectral lines that were not accounted for, which had been lumped into Fleming's B designation. Maury labeled these as classes 1 through 5 at the beginning of her sequence because she noted that the most prominent examples of these, in fact most of these objects, were found in the presence of nebulosity, and she felt this indicated that the stars were most likely recently formed from that material. This is a really bold and important step as it began to tie her classification scheme to something more than just the appearance of the spectral lines. However, as she worked with the spectra themselves, especially in those early designations, she had a really difficult time identifying the elemental sources of those lines in those B stars. And some of those lines, which made this even harder, occurred as emission lines, as we've already noted, and in other stars they occurred as absorption lines. As you can tell, this is really confusing, right? This was one of the major things that held up Maury's classification scheme, and throughout 1893 she struggled to complete the paper that would explain her work to the broader astronomical community. The other issue was that depending on how you worked the classification system, there were either 110 possible classes or, by some less charitable estimations, 154. This is something of a nightmare, as it meant that if the system was broadly adopted, an observer or calculator would have to be familiar enough with the differences Maury saw in different spectra to be able to accurately place stars in the right box, as it were. Now, to be fair, one of the interesting things, something that would become really important a few years down the road, was that only some of the stars showed certain subcategories. For example, that B subcategory we were talking about was only seen in stars from classes 1 through 10, and the C subcategory only appeared in stars classified 3 through 13. When this was taken into account, the number of different occurrences dropped to a slightly more manageable, but still enormously large, 48. As a result of these issues, she and Pickering, as I said, went back and forth through the end of the year, an exchange that on more than one occasion ended up involving Maury's father, the Reverend, before the final draft was completed and handed over to Fleming to see through to publication. Pickering's questions regarding the classification began to affect Maury's self-confidence, and as a result the relationship between the two deteriorated somewhat. This was the reason that Maury decided to take her leave from the observatory to do some travel and to see what other opportunities there might be available to her. This, however, did not end the story of her work. As we said, the hardest thing to reconcile in her analysis were a set of spectral lines found almost exclusively in those stars that had been photographed in and around the Orion Nebula, which all belonged in classes 1 through 5. These Orion lines, as they were called, defied explanation and so caused all sorts of problems as she tried to figure everything out. However, in 1895, the Scottish chemist William Ramsay published the results of his work with the mineral cleveite. This mineral, being radioactive as it contained uranium, though the nature of radioactivity was still pretty much unknown at this time, produced a gas known as cleveite gas when it was reacted with sulfuric acid. Ramsay had been able to show that the gas produced a spectrum that contained a line that matched the helium line Norman Lockyer had identified in the solar spectrum some years before. This not only showed that helium did exist on Earth, but also gave a complete spectrum of the element. Now, what's more important for our story was that the other lines found in that helium spectrum created by Ramsay matched Maury's Orion lines to perfection. While the paper was now too far along in the publication process to make corrections inside of the paper itself, A 6-page addendum was added to the effect that Maury's classification scheme took these into account in reordering Fleming's spectra in such a way that might more accurately account for how stars evolved as they aged. In this way, Fleming's B stars were, in a sense, moved to the front of Maury's series of classes, while the rest were more or less allowed to remain in their same order. This paper was published under Antonia Maury's name as first author in the Annals of the Observatory, and it marked the first time in the history of that institution that a woman's name had occupied that place. Now, the 1895 discovery of the full set of helium lines also forced Hermann Vogel to rethink his classification scheme, and he did this at about the same time as Maury's work was being published. As his scheme was simpler and more in line with current thinking regarding stellar evolution, there erupted a bit of a scientific controversy regarding which system should be adopted by the astronomical community. While some of the back and forth was a bit uncharitable, especially from the folks associated with the Potsdam Observatory, it served to show that there wasn't yet enough information to make a determination as how to proceed. As spectroscopy had evolved in Earth-based laboratories, there had been an interesting pattern that had been noticed. Known as the Balmer Series, the pattern had to do with the determining of the spacing of hydrogen lines in the visible part of the spectrum that hydrogen produced. This pattern was nicely modeled with an equation that used as part of the calculation the subtraction of the number 2 from a larger integer. Actually, if we get into the specific details of the formula, it's actually the subtraction of the square of the number 2 from the square of a larger integer, but we'll neglect that for a moment. In other words, one line could be found if the equation took as a part of the calculation the square of 3 minus the square of 2. The next line could be found by taking the square of 4 minus the square of 2, and so on. This Balmer series was one of those things that indicated that there was an underlying order to the spectral patterns for each of the elements, though the cause for that pattern wouldn't be revealed until the work of Niels Bohr in 1913. As you might expect, these Balmer lines could easily be seen in the stellar spectra, but in 1896, Edward Pickering was looking at the spectrum of a star of the Wolf-Rayet, or O-type, in the constellation of Puppis, and he noticed a really interesting thing. There were a series of lines halfway between the Balmer lines. After measuring the wavelengths of the lines, he tried to see if he could use the Balmer equation to model their locations, and he found that he could if he used, instead of integer values, half-integer values. In other words, 2.5, 3.5, and so on. Pickering believed that the lines were somehow being produced by hydrogen in a way that hadn't yet been duplicated in an earthbound lab. The discovery, however, made 1 year before Thomson's discovery of the electron, prompted Norman Lockyer to suggest, after observing the lines in the spectrum taken from the sun's chromosphere, that the enormous heat of a stellar atmosphere might cause atoms to disassociate in some way to produce things that he called proto-elements. While not exactly correct, Lockyer's idea is remarkably like what would be learned to be the process of ionization, but that's for another time. The other upshot from this discovery was to call into the question the place of the O stars, or, in the case of Maury's classification system, they were called Type 22 stars, at the end of the stellar classification sequence. That is assuming that the sequence has some basis in the evolutionary process that a star undergoes. The high temperatures thought to be required to create the extra half-integer Balmer lines suggested that perhaps these stars might need to be placed at another point. Now, at about this same time, a number of new plates began arriving from Peru. Just as Pickering had used the Draper 11-inch telescope to take single spectra of bright stars in the northern hemisphere, with the conclusion of Maury's work, he decided that a similar effort was needed for the stars in the southern skies to see if the conclusions reached in that paper were upheld. As the first of those single spectrum plates began to arrive, Pickering realized that he would need to designate a specific calculator to work with that project. By this point, the observatory was beginning to attract a number of applicants who had studied physics and astronomy at one of the women's colleges, most notably Radcliffe, which had among its faculty an astronomer that had been trained by Pickering first while he had been at MIT and then later while at the Harvard Observatory. One of these students that was attracted was a woman by the name of Annie Jump Cannon, whose work at Radcliffe's observatory had prepared her particularly well for just such an endeavor. As I expect I'll do a supplemental episode on the lives of the calculators, let me leave the biographical details of Cannon's life to that episode and we'll move forward. Brought into the observatory in 1897, Cannon was given the task of analyzing and classifying the spectra that soon poured in from Peru. Once again, as he had done with Antonia Maury, Pickering gave Cannon free rein to develop whatever classification scheme she wished. As she had been trained in the process of identifying stellar spectra by Fleming, and indeed, she actually imported with Fleming, Cannon elected to work with her letter-based approach. However, in a nod to Maury's more physically based system, she chose to adopt an evolutionary criterion in addition to looking at the changing strengths of the hydrogen lines when setting up her classifications. As such, she adopted a new ordering of the letters to be O, B, and A, rather than the old A, B, all the way to with O at the end. Additionally, she chose to combine several of Fleming's letters, thus simplifying the system, at least at the highest level, to just 7 initial classifications. Her new order was O, B, A, F, K, G, M. There are 2 things I'd like to comment on at this point. One having to do with the philosophy of science, and the other having to do with something related maybe to nomenclature. The first thing is sort of a guiding principle in science we've discussed a bit in previous episodes. When you're attempting to develop models or classification schemes for natural phenomena, one of the things you try to do is keep it simple. It's a hard thing to do, actually, especially when you're down in the weeds of a thing, because you tend to become an expert in seeing all of the little differences and unique aspects of what you're looking at. What you've got to try and do is focus in on those aspects of a system that you believe are truly important and then work with those. Both Fleming and Maury, not being really sure what was important and what wasn't, made systems that were progressively more complex compared to what Secchi had started with. What Cannon ended up doing was scaling that back a bit, especially at the top level of the main classification system. Now, what we do know is that she did develop a method for the finer details that would live at the deeper level, and we'll talk about that in a minute, but her simpler system allowed people to access what she was talking about in a much more intuitive way. It also focused in on the main things so that everybody can understand those, leaving other details until later. The second thing I need to discuss is the long-held mnemonic associated with Cannon's systems. Since the classification designations no longer have the letters in alphabetical order, or in numerical order for that matter, it can kind of be hard to remember which letter happens where. In order to help with this, and one suspects is something of a crude jest, a student at Princeton came up with a little phrase that puts the letters in the right order. You may have heard of it. It goes, "Oh, be a fine girl, kiss me." Now, there's a lot of angst that's been developed around this, so let's take a moment to address that. First, it is likely that the student at Princeton was poking a bit of sexist fun at the situation at Harvard Observatory. Princeton was, at this time, still a pretty tradition-bound institution, and the idea of women doing what was typically thought to be men's work was more than a bit scandalous there. Among the astronomical community at the time, there were more than a few who, instead of looking at the inclusion of women in the scientific work at Harvard as a progressive step in the right direction, saw it as an untoward development, and so nicknamed the group of women calculators Pickering's Harem. As more and more papers were published, however, highlighting the truly revolutionary work being done by those women, this sense of impropriety gave way to envy and jealousy among those people, along with the usual sorts of mocking that accompany such feelings. Now, to their credit, most of the best American astronomers looked past the conventions to the groundbreaking science that was being done and fully supported Pickering's innovations. Though it should be said that it would be decades before many of them or their institutions would emulate Pickering's move towards including women. The phrase, however, has persisted for whatever reason, and so I might recommend the slight modification to, "Oh, be a fine girl or guy," whichever the user prefers, kiss me. For those who find the inclusion of kissing distasteful because, people have cooties or something, there are other phrases that have been developed to help one remember what is known as the canon ordering that can be found with a simple Google search. Canon's work, containing some 1,182 stars and initially published in 1901, turned out to be an important step forward as it formed the basis of the system we still use today. There are two additional things we should say about it, though. One change that Canon made was to drop Maury's line thickness subcategories. This would actually turn out to be something of an error, though dropping them would open up the possibility to think of multiple types of stars, as we will see in a future episode. The second thing Canon did was subdivide each of the classifications, with the exception of O-class and M-class stars, the two on either end of the classification she used, into designations 0 through 9. This would allow for stars that seem to have some characteristics from each of the two groups to be slotted in, say, for example, an F star, when it had lines associated with both F characteristics and G characteristics in terms of its spectra. In this classification system, our Sun is classified as a G2 dwarf, and we'll talk about that last bit, the dwarf part, in a few weeks. Along with the classification scheme, Ms. Canon also set out a set of 48 classification criteria to assist others who would need to use the system to classify stars. These, with some modification, would serve as the basis for training all graduate students in astronomy to do classification of stellar spectra for the next 90 years, until computerized artificial intelligence systems took over that work. My advisor at the University of Florida actually taught the last stellar spectra graduate course there in 1994. Nowadays, spectra are digitized, fed into a computer algorithm where they are pattern matched with a large number of example spectra, and a classification is produced. In my general education astronomy classes these days, my students use a rudimentary form of this to classify about 50 stars as part of one of the labs that they do. While such technologies make the work easy today, as we will see, it was due to the work of women like Mina Fleming, Antonia Maury, and especially Annie Jump Cannon that made this possible. As we bring this episode to a close, let me cite a few of my research sources. The most technical of these is John Hernshaw's The Analysis of Starlight, 2 Centuries of Astronomical Spectroscopy. This is a work only for the really committed historian of science who has some training in these various areas specifically associated with stellar spectroscopy. While it is a quite good resource, the technical detail can be a bit overwhelming, and so I think probably the layperson might want to avoid that. However, for those of my listeners who have a solid scientific background, you'll find some really great nuggets of information in there. My second source has been David Leverington's A History of Astronomy from 1890 to the Present. This is a much more accessible work that is also quite a bit broader and more general in its coverage. It's one of these things that I expect I'll be using a lot as we go forward, as we cover various and different topics in understanding our place in this universe. My final source is Dava Sobel's most recent book, The Glass Universe. Here, Ms. Sobel takes the reader through the history of the work being done at the Harvard Observatory by the female calculators. I think it's an excellent read that is non-technical and full of biographical detail. And I think for you guys, listeners of this podcast, you'll really find it a great balance between the scientific work being done and the people and personalities that are doing that work. While some of the reviews have said it's very, very dry, I expect you all will find it just right up your alley. One note I would like to make has to do with the title of the book, which I find highly evocative. One of the things that Dava Sobel talks about is that these women would only observe the universe through these glass plates. Only one of them would ever look through one of the observatory's telescopes, and only one of them would ever see that sky in the way that someone like, say, Carolyn Herschel would have through the eyepiece of a telescope. Instead, most of them each day came into work and they accessed the cosmos through a series of glass plates, 8 by 10 inches in size. From this universe recorded on photographic plates, they gathered the information that allowed humanity to figure out the answer to the question, what our place in all of this that surrounds us actually is. For them, those plates represented the glass universe. It's really quite remarkable. In closing, I'm recording this on Memorial Day 2017 here in the United States. For all of those listening who have lost friends or loved ones in the conflicts around the world, let me offer my sincerest condolences and gratitude for your family sacrifice. I dedicate this episode of the Scientific Odyssey to the memory of those who gave the ultimate sacrifice, protecting those liberties they held most dear. As a programming note, the next couple of episodes are likely to be supplemental in nature. I would like to take an episode to talk in more detail about the lives of these remarkable women who worked at the Harvard Observatory. I think I would also like to dig a little deeper into what exactly the Doppler effect is, and some of the places it is utilized in the years we're talking about here, from about 1870 to 1910 or so. After that, I'm off to Boulder for the National Social event and some of the activities surrounding that. As always, thanks for taking the time to listen to the podcast, and until next time, full sails on your journey.